Hello everyone, and welcome to today's webinar on Polymer Additive Manufacturing, Microstructure and Failure Analysis. My name is Rena Samsu, marketing at Eurofins EAG Laboratories. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Jennifer Hoffman, Director of Project Management, along with a few of our technical experts, will be answering some of the questions during the presentation, and we will also collect these and address them during the Q&A session at the end of today's talk. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our presenter, Janneke Schneider, Senior Scientist and Project Manager at Eurofins EAG Laboratories.
Good afternoon, everybody. Very happy to be here. So I have been working at EAG for about 9 years. And I specialize in materials characterization. I work with FTIR and XRF spectroscopies, and I handle a lot of interesting projects that involve multiple techniques, such as failure analysis investigations, deformulations, cleanliness analysis, and so on. And as Rena mentioned, I'm joined here by Jennifer Hoffman, who is our new Director of Project Management. In addition, she is an expert in polymer fractography, and we're going to be actually talking about some, SEM images that she has interpreted. In addition, we have Patricia De La Cruz. She is a failure analysis engineer, and she also took some of these beautiful SEM images featured in our talk today. So here's an overview of the webinar. I'll start with a little introduction to Eurofins EAG, who we are and what we do. And then I'll talk about 3D printing, specifically common techniques for 3D printing of polymers, as well as characterization techniques. The bulk of my talk will feature these 4 interesting case studies, where we look at print process optimization, print quality issues, effective print settings on mechanical properties, and our last case study will look at chemical and surface properties of different resins. So what is Eurofins EAG? Well, first, let me say a little bit about Eurofins. Eurofins is a global leader in laboratory testing with more than 58,000 employees, 900 laboratories in 54 countries. Eurofins EAG, it specializes in materials testing, and we've been around for more than 40 years. We have more than 600 employees and about 20 laboratories all over the world. We have 2,500 types of instruments in our labs, and we work with about 4,000 clients. So we're a really large company. We've been doing this for a while. And this is kind of our famous SMART chart. It stands for Spectroscopy, Microscopy, Analytical Resolution Tool. And this is a very helpful guide for figuring out, your technique, analytical spot size, which varies from about an angstrom to 1 centimeter, as well as the detection limit of the technique. And so let's say you need something that's, in the 10 micron range, you can see what techniques are available. This SMART chart is also color-coded, so techniques that give you elemental information are in this dark blue, techniques that give you imaging information are green, and so on. And of course, we have some techniques out here that really don't fit in this box. They don't necessarily have an analytical spot size, such as GCMS or IGA. We sort of consider them bulk techniques. But overall, this is a really helpful tool, especially for failure analysis. You have to understand the limitations of the various techniques in order to choose the right set of techniques. All right, well, what is 3D printing? I'm sure some of you have heard of it. This is very popular. Another word for 3D printing is additive manufacturing. And so it's simply a process of building out a 3D object from a digital model, typically a CAD drawing. In terms of polymer 3D printing, we have 3 different techniques: fused deposition modeling, selective laser sintering, and stereolithography. And I'll go into some detail about these techniques. Essentially, what you're doing here is you're building an object layer by layer. Either you're melting some material and sort of fusing it, or you are doing a photo curing reaction. Oftentimes, at the end of the print, you'll need to do a surface treatment to reduce roughness or remove some sort of supporting structures. The reason why this is so popular is because, and especially with polymers, is you have such a variety of materials that you can use. You can look at rigid polymers, elastomers, biopolymers, and there's even 3D printing with cells. In addition, you can reinforce your materials with a variety of fillers, such as glass fillers, flame retardants, colorants, and so on. So you can make these nice, robust structures fairly quickly. This is very useful for prototyping. You know, if you wanted to make a plastic part using injection molding, you'd have this die. It's very complicated and very costly. And instead of using 3D printing, you can do it very easily. You can also design quite a bit of complexity and fine structure. You can customize very easily, and this is a very sustainable, model because you're not using so much material. And 3D printing is getting more and more popular every day. It's used in dental and medical. For example, this is like a prosthetic hand that's 3D printed. So if you lose a limb or something, you can easily print a new one. Obviously in tooling and in fashion, aerospace is starting to 3D print with, sophisticated resins, and automotive, defense, all sorts of fields. I mean, we've heard about 3D printing of guns, which is a bit unfortunate. So in terms of different 3D printing methods, the most popular, or one of the most popular, is called fused deposition modeling. Another name for it is fused filament fabrication. And so in this method, you have a filament that you use, and it's fed through rollers, and it goes through this heated nozzle and applies this deposited material on a hot bed. And it applies it layer by layer, again, depending on this CAD drawing that you have. You use software to create slices, so that breaks this digital model into printable layers, and then you just print layer by layer. So common failure modes with these kinds of materials is you can develop defects and voids, you can have delamination between layers, and in general, you can have poor print quality that doesn't look aesthetically pleasing. Another popular method is the selective laser sintering. So here you're using a powder, and so you have a high-powered laser that is sintering, sort of fusing these powders together into a specific shape. And again, you're using this CAD drawing that's broken up into sections. And so the software knows how to, increase the layer by layer to create your desired material. Here again, you can have defects, you can have a granular structure, you can have poor mechanical properties. Typically, resins like nylon are used, which have some crystallinity, and so if you don't heat it just right, you're going to change the crystallinity profile, and you'll have poor mechanical properties. And again, you can have a poor print quality, aesthetically not pleasing. And finally, this is a very popular method. It's one of the first commercialized 3D printing technologies. This is stereolithography. So here you're developing this 3D structure by photo curing a monomer using UV light. And again, CAD is used to create your sections. In this case, because you're using a monomer, you'll often need to wash the part with solvents, remove unreacted materials, and so on. And often you will have some support structures here as well. Common failure modes with this type of printing is contamination. Contamination can cause poor curing and, not give you the shape that you want. You can also have defects and voids. So when it comes to trying to troubleshoot these issues that I brought up, typical issues, you have a variety of different techniques. to characterize the materials. And it might start with the raw material. It might start with just that monomer, that powder, that filament. And you might want to know, what is it made out of? And you have techniques like FTIR for your transform infrared spectroscopy to tell you the chemical composition, the molecular structure. You have techniques like XRF, which can tell you the elemental breakdown and parts per million detection limits. I mention these because we will be featuring them in our case studies. In addition, for polymers, thermal and morphological properties are really, really important. Like I talked about that the crystallinity. So that's something that you can measure with differential scanning colorimetry. Or you can also see if your material is becoming less thermally stable with TGA, thermogravimetric analysis. All of that can give you some clues about, what raw material is starting with, and then of course the finished part. With the finished part, you have a lot more options in terms of techniques. And so, for the finished part, it really depends on what is the application. Is this part used in a mechanical support role, or is it just a housing or something like that? What's important, that's kind of what you test for. All right, well, now we can start with our case studies. And here's a little overview of the 4 case studies. The first one we're going to talk about involves acrylonitrile butadiene styrene copolymer, a very popular resin, ABS. And here we look at the effects of print settings on mechanical properties and physical properties. Our second case study is concerned with polycarbonate. Now, both of these polymers are amorphous thermoplastic materials. And here we are looking at print defects. We use chemical characterization and imaging to understand the cause of these. And our last 2 case studies are concerned with polylactic acid. This is actually a biodegradable crystalline, semi-crystalline polymer. So it's a very robust material. And we look at the effect of print settings on mechanical properties. We also do a little vapor exposure study and look at the surface finish. And then we have the last case study is concerned with 3 different PLA resins and trying to understand their chemical and surface properties. Okay, let's start with our first case study. So here we look at ABS, which again is one of the most widely used materials in 3D printing. And if we're going to print anything, we might as well print a dog bone, because a dog bone is used in mechanical testing, and we can understand if our materials are strong and if they have the properties that we need. So, and this is exactly what we did. This is a really great way to optimize your print processing conditions. So in this study, this is our dog bone that we created. We varied various parameters such as layer height, the print speed, and something called the extrusion multiplier, which is basically the flow rate of the resin. And to evaluate, the results, we both did some mechanical testing, which I'll show in a second, but we also did cross sections of the thinnest part of this dog bone. And as you can see, some samples had a lot of pinholes and voids, while others were much better. And ultimately, what we found was really, really interesting. So the amount of these holes in the cross section really, controls the mechanical properties. So when you have a lot of porosity and voids and so on, your material is a lot less dense. And we saw almost a linear relationship between the density of the material and the strength. And so the most dense materials were always the strongest. And so these are, materials that were 3D printed. And here we have some materials that were injection molded. And you can see there's quite a big difference. So these 3D printed parts are not really matching the mechanical properties of 3D of injection molded parts just yet. We also did a series of other experiments. So we wanted to see, what would happen to these dog bones if we expose them to heat 90 degrees for up to 2 weeks. And we did the experiment both in an unstressed condition where they can lay freely on these metal bars, and also in a stressed condition where they're sort of pushed under the bar, so they're positioned in a specific manner. And what we found was very, very interesting. So as you can see in this picture, the injection molded samples, in the unstressed position, they sort of turned in different, they distorted in a random fashion. So they're turning, one way or the other. For the 3D printed samples, they all distorted in the uniform fashion. So they, they all are pointing upwards. And what that tells us is something really important. It tells us that we have likely residual stresses that are being released due to the heating process, right? And the stresses come from the fact that there is a temperature gradient, as we're doing the print. So this is really hot and this cools down. And so we have residual stress built up at the top of the part. And that's what we're trying to do. When we're heating it, we're relieving the stress. The other thing that was really interesting is we took these samples that were heated, for 1 week and 2 weeks, and we looked at their mechanical properties. And with the injection molded samples, we saw a drop in the mechanical properties, a slight drop, especially when they were stressed. There was a much more significant drop. The opposite was seen for the 3D printed parts. After heating for 1 week, we saw a pretty large increase in the mechanical properties. And of course, that actually decreased after 2 weeks. So that suggests that maybe 2 weeks is a little bit too much heating time. But 1 week, we saw a pretty marked increase in the mechanical properties. And of course, it was also true for the stress samples, but not as much. So that kind of tells us that this heating process can close up some of these pores, some of these voids, and improve the mechanical properties. Okay, I will move on to my next case study. This one's also really interesting, involving the polycarbonate material. So here we just bought a new spool of filament, and dried this filament for 96 hours at 67 degrees in a vacuum oven, standard procedure before the print. And we start printing and we see, really poor print quality. This is nice and smooth, and this is quite rough and, has this speckled appearance. So something is really wrong. And this is kind of showing the print direction. When we did some microscopy, we realized that the good area of the print had a really nice smooth finish, while the bad area had all sorts of loose fibers and, kind of a messy interface, messy, poor contact area with the different layers and so on. So, this is the evidence of this poor print quality at the microscopic level. We did some chemical testing to try to understand what might cause that. So this is for FTIR, Fourier transform infrared spectroscopy. We looked at different filaments from different batches, and the peaks that we saw were typical for polycarbonate, right? So polycarbonate has aromatic and carbonyl and alkene functionality and so on. Double bond functionality, aromatic functionality. So the peaks that we see are quite typical. Now, we did find in one case in the bad batch a little bit more of this hydrocarbon species. That's probably oil or grease or something. But the important thing is we didn't really see any hydrolysis. We didn't see any breakdown of the polymer structure, at a high level. And so we think that the issue really is process related. And again, when we went to examine the filament at a microscopic level, we realized that the first 50 to 60 meters of the filament was no good. And that happens a lot. That the beginning of that filament is not a very good material and will do a poor print. But you can see again with these large voids that are present in the bad part, and much smaller voids are in the good part. Okay, so now I will move on to our third case study. This is the one that Patricia worked on quite a bit. And so here we are working with PLA. This is our biodegradable polymer. And we're going to vary a couple print settings here. We're changing our pattern, so we can have this interesting cubic pattern, or we can have this trihex pattern. And I've heard in the past that this is actually usually some of the best, the trihexes results in better mechanical properties. At least that's what's been reported. We also looked at different infill densities, right? So how much material is added. And as in the previous studies, we printed dog bones, and then we also looked at their fracture surface. And what we found was actually a little bit surprising. It turned out that the cubic pattern was a lot stronger, so much higher stress at break, as well as tougher, larger area under the stress strain curve, and even more ductile, going down to almost 6% strain compared to the trihex infill here. We cap out at around 3% strain, and we don't nearly get to the strength. So cubic is the better pattern, and we wanted to understand, why that was on a microscopic level. And so we did some SEM imaging of the fracture surfaces. And so what you see here is with the cubic pattern, you have a lot of necking and yielding. You have macroductility. In the trihex, we have a different kind of fracture. We have a brittle fracture, and you could see these lines in yellow indicate the direction of crack propagation. And this is at 1 magnification, about 100x. Now, when we go to 400x, relatively the same story. Cubic is very, very ductile, and trihex is still brittle. And only at the very highest magnification, we can see this taffy-like threads. That's what we consider ductility, the microductility. But cubic is ductile throughout the structure. So that suggests that, with this trihex, we are actually sort of maybe embrittling the material a little bit, while the cubic is very, very ductile and leads to excellent mechanical properties. Another experiment that we did is, this is actually top-down imaging. We took the PLA samples, and we exposed them to a vapor of lactic acid. And what you see is, we have a smoothing of the surface due to the vapor of lactic acid, and that's obviously lactic acid and polylactic acid. They kind of like each other, and so yeah, a lot of these sort of ridges that you see on top are kind of smoothed out. We also did it to another polymer, PETG, and you can see that even more dramatically. All the surface roughness goes away due to the vapor from the acid. So this is actually a really nice idea for smoothing the surface of a 3D printed part. Simply expose them to acid vapors. Okay, I am now getting to my fourth case study. And here our goal was to compare 3 different PLA resins. Again, this filament you can buy on the market, and every supplier, is a little bit different. So we wanted to understand, what is the difference? Our first sample is called PLA, and that is our regular PLA, sort of, we call it RPLA. In addition, we have something called toughened PLA. Again, don't really know what makes it toughened, but apparently has better mechanical properties. And then we have a copolymer of PLA and PHA. And PHA is polyhydroxyalkanoate. So this is a biodegradable polyester type of material. And in this case, we're really interested, how much PLA versus PHA we have. So we have these 3 resins, and we analyze them using 3 different techniques. So first, we're going to do FTIR, which we already kind of mentioned earlier, that tells us about the polymer chemistry. Then we have some XRF data that tells us about fillers and additives. And finally, we use contact angle measurements to look at the hydrophobicity and surface roughness of the 3D printed parts. So this is actually one of the 3D printed parts that we dipped in water for our contact angle measurements. You can see the color is blue. So let's start with FTIR. So this is the structure of PLA, and here is PHA. So this is more like an aliphatic polyester, and it turns out we really did not see very many differences between these three resins. So that suggests to us that the PHA content is probably pretty low. Now, I should say a word about FTIR detection limits. FTIR can see, somewhere between 5 and 20 weight%. So it's not a particularly sensitive instrument. So, if you have about 5 weight% PHA, you might not see it very easily by FTIR. We did see a small difference here in the CH region, which I blow up here, and you do see some extra peaks in the tough PLA resin. Okay, now moving on to XRF. So just let me briefly say XRF is X-ray fluorescence. We shoot X-rays at the sample and get their elemental composition. We get both the bulk elements as well as the traces, and that can be really interesting for evaluating differences between various resins. So with our, you can see that the carbon and oxygen levels are generally very similar, but for example, the regular PLA had a much higher sodium, aluminum, silicon, sulfur, and potassium content. Similarly, we find that the tough PLA had, significantly more chlorine than the other samples that we looked at. And this could be actually very critical if you want to make sure that your part doesn't have any chlorine, because chlorine will react negatively with your process. That's something that you really want to know. And we can get that information with XRF. We can also see that our samples have a trace amount of titanium, and the color blue we think is coming from the copper, right? And you could see the copper content actually varies quite a bit from 470 parts per million to 110 parts per million. I should mention that, for copper in this type of analysis, our detection limit is about 4 parts per million. So this is something that we can quantify quite easily with this technique. Okay, now moving on to the contact angle measurements. So let me explain this a little bit. This is a pretty unique technique. I think people are familiar with the static contact angle, where you put a droplet of water and you want to understand how that water spreads on that surface. If it spreads well, we consider that surface hydrophilic, and that means you have a low contact angle. If it balls up, like for example with Teflon, we consider that surface hydrophobic, and that's going to have a higher contact angle of 90 or even up to 180. And so that's a static measurement, right? How well the water spreads. Now with this dynamic measurement, we are doing something slightly different. We're not putting a droplet of water on the surface. Instead, we're taking our sample and we're putting it into the liquid, and then we're pulling it out, right? And when we put it into the liquid, we are measuring the advancing angle. So that's just what is the surface like before we wet it. And when we pull it out, that's the receding angle. So how has the surface changed now that it's been dipped with water, now that it has some water on the surface? How wettable is it now? And the difference between the ascending angle and the advancing angle and the receding angle is contact angle hysteresis. So that's telling us a little bit how the surface is transforming due to water, right? And so with these samples that we looked at, we actually found a pretty large hysteresis, right? So you could see our advancing angle, one of our measurements about 97, another measurement's about 99, so pretty close. And then the receding angle drops to 59 degrees for both measurements. So that's a pretty marked decrease. So what exactly is happening? So we also looked at, so this is the story for the regular PLA. We looked at the copolymer, and the copolymer had a much smaller contact angle hysteresis. So the advancing is about 83 and the receding is 63. In the literature, actually, that's the numbers that we would expect. And as we mentioned, this PHA PLA copolymer probably doesn't have a whole lot of PHA. It might have a little bit. Maybe that's why the contact angle is lower. We would expect, PHA to have a lower contact angle because it is a more hydrophilic material. But actually, our hypothesis here is that surface roughness plays a large role here. For our regular PLA sample, the advancing angle is really high, and the reason for that is likely because it's a very rough material. It's a very rough surface. And then when that surface is wet, now all the numbers kind of line up, and all the receding angles for this material are rather consistent. So of course, we can go further with this. We can actually do some optical profilometry on the surface and see if this is actually accurate, if the surface roughness is really different. And that's what's causing the contact angle to be so high, because the contact angle is not simply how the hydrophilic the surface is, it's also really the surface roughness. It takes that into account. Okay, so I completed discussion of the 4 case studies. And I just want to now say a few words about our approach to failure analysis. How do we try to solve these problems? We get a lot of interesting problems, and what do we do? So we always want to start by documenting the failure. What happened, right? We take optical pictures, images, maybe microscope images if needed, but we want to understand, is it a broken part? Is it a cleanliness issue? What is the failure? And then we want to compare a good and a bad part. And we want to do a variety of tests, a lot of the material characterization tests that we talked about today, as well as, functional tests, like how is this part used? Is it the mechanical part? Okay, we can do some mechanical testing, but we want to compare a good and a bad. Where is there a difference? What can we see as something that stands out? And so, sometimes we do FTIR, we don't see a difference, but we do thermal analysis and we do see a difference, and that might lead us in a certain direction. So once we've gathered all of the clues, all of the evidence, then we actually want to try and reproduce this failure. So we want to take a good part and see if we can induce the same kind of failure with the same kind of failure fingerprint, right? And then we can be assured that we've really found the cause of the failure, and we can reproduce it, and then we can find nice solutions to mitigate the failure, right? So that's generally our approach. Okay, so I hope you've enjoyed this presentation. We talked about different kinds of 3D printing techniques. I focus on 4 case studies that highlight issues with density and porosity and its effect on mechanical properties. We looked at an example where we had failure due to bad filament. We also examined how 3D printing settings, such as using cubic or tri-hex, will affect mechanical properties. And we could even explain some of those mechanical properties using SEM imaging, using fractography. We also showed the effect of chemical vapor exposure on smoothing the surface and making a nice finish. And we looked at a case study that compared nominally 3 very similar PLA resins, and we were able to sort of tease out differences in these materials based on their chemical structure, their additive profile, and also their surface properties. And of course, I just talked about the failure analysis approach that we use here at EAG. Okay, so I just want to wrap up and say, I hope that you will be interested in working with us. We love to solve problems. We love to solve puzzles. And why EAG? There are many different reasons, but client confidentiality is core to our business. It's very important to us. And as I mentioned earlier, we are truly a global leader in this field. We have so many different kinds of instrumentation, and also we have a lot of expertise. We have people who have been running instruments for decades and have just so much knowledge about what data they're getting and how to properly analyze something. You don't have to actually know how to solve the problem to work with us. You can just tell us about your problem and we'll figure out a nice set of analytical techniques to help you solve it. In addition, we are ISO certified 9001 and 17025, so we're fully accredited. And like I said before, we just love this kind of work. We are science geeks, and this is really fun for us. All right.